All right, so we'll get started here. Let me. Let's just talk a couple of things. Okay, so homework 1 is due tomorrow. So make sure you submit that. And then I've released homework 2, and that will be due a week from tomorrow. Okay, so that will cover basically the stuff we covered this week. So that's what we've got. All right. Okay, so today we will talk about gradient descent. Gradient descent is an optimization method. All right, and so so far what we've done is we have used this as our loss function, and the loss function has been the mean squared error, which is this. And to find the minimum, what we did was we found the derivative. We set it equal to 0, and then we solved, okay? And you know, this loss function, it's pretty simple. It's not too hard to find the derivative. And even in matrix notation, we can find the derivative relatively easy. However, you know, the loss function at other times can be a lot more complicated, or you might just have another function that's more complicated. And maybe you can find the derivative. A lot of times taking the derivative isn't too terrible, but sometimes figuring out where the derivative is equal to 0, right? Like solving for where the derivative equals 0 can get really hard, might not even be possible, okay? And so, so what we're gonna do in these cases is we can use a computational method to help us find a local min, right? And so the computational method that we're going to talk about today is gradient descent, okay? And so, you know, when we have a loss function like this, okay, this, it's the actual value minus what our model predicts. And what the model predicts is based on the parameter estimates that we're using, based on the values of W0 and W1 that we're choosing, or whatever it might be, okay? So the important thing to remember is that we're treating the data as fixed, okay? And what we do is, you know, there's only 2 parameters to estimate in linear regression, slope and intercept, but then, you know, when we get more complicated models, you know, there might be like 10 parameters to estimate, okay? And so the function that we're optimizing over is going to be a 10-dimensional function. So however many parameters you have to optimize, that's how many, that's the dimensionality of the function that we will that we're optimizing here. So in Wednesday's lecture, I'm going to introduce neural networks, and in neural networks, you're going to have lots of parameters. But the overall idea is you're still trying to optimize the loss function. It's just that the loss function is now a function of high dimensionality. If you took 102A with me, I covered coordinate descent. I don't know if you guys remember that. And for those of you who took 102A with Professor Wu, did you guys learn coordinate descent? Yes, no, maybe? I don't know. No, you don't think so. Okay, that's all right. You don't need to know coordinate descent in order to do gradient descent, but I was just curious if you had seen, you definitely covered unidimensional optimization, right? Like Newton's method? Yeah, okay. All right, so yeah, Newton-Raphson and secant method and stuff like that. Okay, so, well, anyway, you don't need to know coordinate set, but we'll look at gradient descent, and this is how it works. Okay, so if you think about a univariate function, okay, the derivative represents the slope of a tangent line, right? So if you've got some kind of parabola, you know, the derivative represents the slope. Okay, if you have a function of multiple variables, right? So if I've got a 2-dimensional function, then the response is going to be a surface, right? So I've got some kind of 3-dimensional surface. Oh, you know, right? You got your you've got your x1 and your x2, and then you've got some kind of surface sitting on top of that. And the gradient is going to be a vector in 2 dimensions, pointing in 2 dimensions, that shows the direction of greatest increase at some location x, okay? And the magnitude of the gradient is the rate of increase in that direction. Now, if you have, I can like draw a 2-dimensional function where you have a response, you know, a response is, you know, the 3rd dimension, and we can show the gradient there. You can have higher dimensionality, but it's just we can't represent it in a way that our brains comprehend, right? So once you have a function of, say, 5 variables, now we are in 6-dimensional hyperspace, right? You've got the input is five dimensions, there's an output, and so to graph that, you've got this 6-dimensional hypersurface, which you know, our brains can't really comprehend. So, or I don't know, maybe some of you can picture this in your head, but you know, I myself am limited to just picturing things in 3 dimensions. So, but the idea will still generalize in that we've got, I can draw the example where we have a 2-dimensional input and you know, an output. So the picture, the surface exists in 3 dimensions, and you know, just kind of also the analog exists in higher dimensions as well. Okay, and basically, if you imagine some kind of surface, right, kind of like the surface of a map or something, is that in gradient descent is that we're at some location x, and we use gradients to find the direction that points uphill. Okay, the gradient always points to the direction of greatest increase. And if we move in the direction that's opposite of uphill, then that means we're going downhill, right? So if this way is up, then we just go in the opposite direction, that's going to be down, okay? And so we just go, we take a step and we go downhill. And then after we take a step, we reevaluate and we say which way is uphill, and I say, oh, that way is still uphill. So then we take a step downhill, okay? And we just repeatedly take steps downhill. And if you do that, you should reach the bottom of the hill, or at least, you know, the bottom of some kind of valley, okay? And so you can think of this as just kind of like having, you know, some surface, some map surface, and then you just take a ball and you set it, and then the ball will just roll downhill, okay? And that's kind of like how it is, okay? Each, you know, we take a step downhill, and then we just keep going downhill, downhill, and downhill, okay? And so the algorithm for gradient descent is incredibly simple, okay? It's represented very simply. And so this is all it is, okay? We have some function f of w, right? It's like our loss function. This is a multidimensional function. Its input is w. Input is a vector w of, you know, d dimensions, okay? We have a vector of d dimensions here. And we will say we are at some point at time n. So we have vector w at time n, and we're going to choose the next value. So w at the next iteration at time n plus 1 is going to be our current location, w at time n, minus the direction of the gradient, okay? So nabla f represents the direction of the gradient that, that points in the direction of uphill. And we just basically say, well, if this goes uphill, then we go in the opposite direction. That's why we subtract it. So this is going to be the gradient at location w sub n, okay, w at time n. This is the direction of going uphill, and we're going to subtract that. We're going to go in the opposite direction. This gamma here, okay, and sometimes we will see a lambda value, okay? The gamma here is just a scaling factor. It's a positive value, and often this is a value less than 1 to kind of just, because usually, oftentimes what happens and not always, but often the gradient is a very big value, and it says you should, this is the magnitude of the gradient is quite big. And so we just scale it down and we say, you know, because if you take if you multiply, remember the gradient is going to be a vector, okay? The gradient is a vector, and if you just take a scalar, just a small value here, you're just shrinking the size of that arrow. The direction is still the same, okay? But you're just shrinking the size of the arrow. So all we're doing is we're just taking our current value and then subtracting off the gradient at that location. Okay, so is this a constant learning rate? Okay, so we are going to, in our course, we're just learning simple gradient descent where this learning rate remains constant, okay? Now, if you take, say, a neural networks class or another machine learning class, there will be modifications of this algorithm where gamma is not constant. In the beginning, you take big steps, or in the beginning, you take small steps, and you know, and as time goes on, the size of your step changes. So that's a thing that that can happen. But in our class, we're going to just leave this as a constant. Okay. If essentially, would we want, so another question, so essentially we would want to take a smaller step if we use the constant gamma. So what happens, and I'll show you, is that as you approach the bottom of the hill, okay, because the gradient is equal to the kind of the steepness of the hill. The magnitude of the gradient is equal to the steepness of the hill. So in the beginning, where the hill, like, imagine this bowl, okay? Imagine this paraboloid bowl, where at the bottom, it's, you know, there's still a little bowl, but it's quite shallow, okay? But as you go out, the edges are quite steep. So at the edges, the magnitude is really big, okay? So you're gonna take huge steps in the beginning, and then as you get closer to the bottom, okay, it becomes more and more flat, and the gradient will get smaller and smaller and smaller. So we will see this happen, okay? We'll see this happen. I don't know if that was your question, but we'll take a look, okay? I think with some examples, this will become more clear, okay? Is that here, and again, it's just, you have your current value of W at time n, and you're just gonna subtract off the gradient at that location multiplied by some scalar, okay? And that's gonna give you the next value, all right? And then you just repeat, you just iterate over and over and over. Okay, so for illustration, I've got this arbitrary two-dimension function. This is not a loss function, this is just some function. So I've got x1 squared minus 2x1 minus 0.5 x1 x2 plus 2.5 x2 squared. Okay, so this is a function of two-dimensional x. Okay, so here's our function of vector x, which exists in 2 dimensions. And the gradient of f, that's nabla f, okay, can be found analytically using calculus. So the gradient of f is going to be another two-dimensional vector. Okay, it's the vector consisting of the partial derivative of f with respect to x1 and the partial derivative of f with respect to x2. So the partial of x1 squared with respect to x1 is 2x1 minus 2, and then this thing is going to become minus 0.5 x2. Okay, and then there's no x1 term, so that drops out. And the partial derivative of this with respect to x2, this will go away, this drops out. This is going to be negative 0.5 x1 plus, and then the derivative of this is 5x2. Okay, so this is a, there's two values in this vector. Okay, one is this function, and then the other is this function. So this is the gradient of f. Okay, it's a two-dimensional vector here. All right, and so if I create a contour plot of this function, okay, it's a paraboloid surface, okay, and so it looks like a bunch of ovals, and it's here's a kind of a three-dimensional plot of it. It's a, I don't know, just imagine like a salad bowl, okay, or a fruit bowl or something, okay, but a little bit elliptical. So it's not perfectly round, and it's just kind of like this bowl. And basically what we're going to do is we're going to basically put a marble on one side of the bowl and then just let it roll down, okay? Except the difference here is that with physics, the marble has mass and it has inertia. And so it will continue, like when it rolls past the center and starts climbing up the other side, okay? That's not gonna happen here, okay? It's, there's no inertia here. There are actually, I should mention, there have been developments of like modifications of gradient descent that include inertia, but we're not going to cover that, right? Again, if you take a graduate level course in neural networks and stuff, you'll probably learn all of these other things. Okay. All right. So let me just show you how this would work, right? So let's say we start at this location, -5, 4, right? Which is actually, I think right here. Okay. So if or -5, 4 is going to be right up here. Okay. So sorry, so -5 is right here, -4. This is we're going to put a dot right here, up in this kind of top corner here, and we're going to say, all right, which way is uphill? Uphill is, all right, if this is the bottom of the hill, uphill goes in this direction, right? Which way is the steepest descent? This is going to be uphill, and we're going to go in the opposite direction, which will point in this direction, which will be what is downhill. Okay, and so to find the gradient, we plug in -5, 4. So the value of x at time 0 is going to be this, -5, 4. We plug that into our formula for the gradient. So the gradient is 2x1 minus 2 minus 0.5x2. We plug in -5 for x1, 4 for x2. I get -14, comma, and then the other value. Remember, this is the partial with respect to x2 is going to be -0.5x1 plus 5x2. I plug in -5, 4, and I get 22.5. Right? Just want to make sure we're following everything. Okay. So remember, here's the two-dimensional function. I took the derivative with respect to x1. The partial with respect to x1 is over here. The partial of this with respect to x2 is over here. And then now I'm just plugging in -5 and 4 into the partial with respect to x1, and I get -14. I plug in those values, and I get the partial with respect to x2, and we got this. All right. And then, so this is my gradient, okay? And so the next value is we take our current value, which is -5, 4, and we're going to subtract off gamma times the gradient. Okay, so here I'm using a gamma of 0.1. I just arbitrarily chose gamma equal to 0.1. You could choose whatever value you want. I picked this because it's simple. So I'm going to take our current value, -5, 4, and then we're going to do gamma 0.1 times the gradient. The gradient we found up here to be -14, 22.5. Okay, so when I multiply -0.1 times this becomes +1.4 and -2.25. So now I'm going to add this vector onto this vector. And so -5 plus 1.4 is -3.6. And 4 minus 2.25 is 1.75. Right? Gamma being positive means we go uphill. So we're always subtracting off gamma times the gradient, okay? So gamma positive, it has to be a positive scalar because a negative scalar would flip the direction. We're flipping the direction, okay? And so if we added the gradient, okay? If I didn't subtract it, if we added the gradient, we would keep climbing uphill. The gradient always points uphill. That's just how the gradient works, okay? So the gradient points uphill, so we're subtracting it, and that takes us downhill. Okay, if I wanted to do this in R, I could, all right? So this is the original function, and so here's our original function, x1 squared minus 2x1 minus 0.5x1 times x2 plus 2.5x2 squared. And then the gradient is going to return a vector, where the first component is 2x1 minus 2 minus 0.5x2. And the second component is 0.5x1 plus 5x2, okay? And so here's how I can code it up in R. And if I plug in negative 5 comma 4, this is the gradient at our start location, and then the ending location. If I take the start minus gamma times the gradient, then I would get the same value that I calculated, negative 3.6, 1.75, which is what I got here, negative 3.6, 1.75. Right. So I want to make sure everyone's okay with how we got these values, negative 3.6, 1.75. All right, it says if we restrict gamma to be negative, we can add the last term rather than subtract. Yes, I mean, it's the same idea, okay? Generally, the accepted convention is we say gamma is positive and we're subtracting off the gradient. That's just kind of the general convention. But you're right, you could swap up and say this is positive and this is negative, and you get the same thing. Okay, so we started out at negative 5 comma 4, and this is our ending location, negative 3.6, 1.75, okay? And we can see this basically climbs downhill, all right? And so we have gone downhill. And then now we are at this location, negative 3.6, 1.75, and we would iterate, okay? So now my start location is negative 3.6, 1.75. I'm just going ahead and using the R function rather than going through the work of calculating these all by hand here. All right, so the gradient at negative 3.6, 1.75 points in this direction. It says go negative 10 and negative 10.075 and 10.55, okay? And what we're gonna do is we are going to take our starting location, which is this point in 2D space, negative 3.6, 1.75, and we're going to subtract off gamma 0.1 times the gradient, okay? So 0.1 times this is going to be negative 1.0075. So if I do negative 3.6, basically plus 1.0075, I'm going to get negative 2.5925. And then here I do 0.1 times this, which is going to be 1.055, and if I do 1.75 minus 1.055, I get 0.695. All right, so after the next iteration, we're going to end up at negative 2.5925, 0.695. So I'm taking our starting location and subtracting off gamma times this gradient. Okay, so we're doing 3.6 minus 0.1 times this is this. 1.75 minus 0.1 times this is this. All right, so, okay, so we have a couple questions here. It says, later, can you give us an example where R finds the derivative for us? And then we plug in values to that stored gradient. Okay, so R can't find the derivative for you. We have another question. What if we can't find the derivative analytically? And then we have another question that basically says that. So, yes, so I will cover that. Ideally, you can find the gradient derivative analytically, okay? You can find the gradient analytically, but in some cases you can't, and there are workarounds for this. It's going to be slow, okay? So there's something called numeric gradient calculation, and I will talk about that, all right? So there is a way to find or approximate the gradient without doing it analytically, and I'll show you, okay? So, so this is what we have. So you find the gradient, and we take our starting location, our starting location here, find the gradient, and we subtract off gamma times the gradient. And this is going to be our ending location. So I'm going to plot negative 2.59 and 0.695. Okay, and that's right here, negative 2.59 and 0.695. So I've taken the step downhill. That was my first step. My next step goes from here to here. Okay, and I can just repeat this process. So now I'm going to start here, and then I take the gradient, subtract off gamma times the gradient to get a new ending location. And so this is a loop of 20 iterations. I start at negative 5 comma 4. This is my start location. And basically, I'm going to add into locations, each row I'm going to add my x vector, okay? And each x vector is the current x vector minus gamma times the gradient, where I calculate the gradient at the x vector at that time. And each time with each iteration, I update my x vector, and I just iterate this, repeat over and over and over, okay? And then when I'm done, I'm going to plot all of the arrows that start at one location and move to location I plus 1, okay? And so when I do that, this is what the end plot looks like. We start off at -5, 4. We go downhill. Here's this location. We find the gradient here, and we take a step downhill. And then we find the gradient here. We take a step downhill. We find the gradient here. We take a step downhill. And we continue. And you can see the size of each arrow as we get closer to the bottom gets smaller and smaller and smaller, right? And what's happening is that the surface becomes more and more flat. So the magnitude of the gradient gets smaller and smaller, because the magnitude of the gradient basically is an indication of how steep the surface is, okay? And so as we get towards the bottom, it gets less and less steep, right? The bottom of the bowl is fairly smooth down there, okay? Yeah, there's still a little bit of contour, but it's the magnitude of the gradient gets smaller and smaller. And so the steps that we're taking get smaller and smaller and smaller. And so technically, it's going to require an infinite number of iterations to reach the true minimum. But at some point, it just gets smaller, right? It's like cutting the distance. Like if you cut the distance in half every single time, cut the distance in half, you're going to get closer and closer and closer and closer and closer to the limit there, but you never actually reach it, right? So that's kind of what happens, is that, you know, as we get closer and closer and closer to the true minimum, where there's the gradient is 0, you know, the steps get smaller and smaller and smaller. And that's okay, right? Is gradient descent guaranteed? Okay, so we have a couple questions. What happens in case where there are multiple local minima? How do we ensure the function reaches the global minimum and not a local one? All right, so that's a problem with gradient descent. There's no guarantee that you will find the global minimum, okay? So if you have this curvy surface, right? So gradient descent is equivalent to just taking a ball, setting it on a hill, and letting it roll down, okay? Now, if in a complicated surface where there's like different valleys, there's no guarantee that you set the ball and it's going to find the lowest valley. It's going to go down and it's going to reach the bottom of the valley, and it's going to stop. And you say, oh, well, I hope I picked a good starting spot so that it ended up at a low point, okay? But if somebody else picks a different location and rolls their ball down the hill and it reaches the bottom, they might have picked a better starting location where their minimum is lower. So there's no guarantee. There's gradient descent comes with like no guarantees, okay? So no guarantee that it's gonna be the global min, okay? So what you can do, yeah, one strategy is you try gradient descent at a bunch of different starting locations, okay? And if they converge to like the same location, then that's probably a good indicator. Or at least if the value at that bottom location is pretty good, then it's a good case. If your loss function is what we call convex, then that means there's often you know, only like one global minimum. That's actually not true. So you know, convex loss functions like the mean squared error generally have good convergence properties, but again, not guaranteed. So we can't guarantee that it's going to find a global minimum, okay? Another question, is gradient descent guaranteed to converge? No, I will show you examples. Even on this simple example, we can run gradient descent and it won't converge, okay? Is gradient descent the steepest descent? Yes, gradient. So another term you hear is steepest descent algorithm, and this is the same. Yeah, gradient descent and steepest descent algorithm are the two names for the same thing. Okay. Yeah, yes, that's one strategy, is you can loop gradient descent over different starting spots, take the minimum of all of those things. Okay. All right, good questions here. All right, but we can see the effect of, with each step, it gets smaller and smaller. Okay. So here is another question. Is there any criteria to know if gradient descent will work or not? No. There's no magic thing that says, okay, I picked all of these things right, and therefore gradient descent will work, okay? This is a big area of research and trouble and problems with current machine learning models, is that we don't know when things are gonna work out. And so there are different algorithms that some have better convergence properties than others. And they're, and when you quote train a model and you're searching for the minimum, there's known to have all sorts of loss function issues, and you kind of monitor the loss function, and if it starts acting wildly, then you say, all right, let's halt it, or we'll let it keep running, things like that. So so anyway, I wanted to show you what happens when you pick different values of gamma. Okay, so this is a plot where I had gamma equal to 0.1. Here I could choose a smaller gamma equal to 0.03, and basically each step is just even smaller, right? So when you take a step downhill, you're just taking tiny little steps, and you're going downhill, okay? And that's just gonna mean it takes more iterations, right? So this is after 20 iterations of gamma equal to 0.03, and this is as far as we got. We haven't reached anywhere close to the minimum, because each of our step sizes are a lot smaller. Okay, here's a bigger gamma 0.15. I've taken, my first step is huge, okay, and I go like this, okay. Now, if you take a gamma that is too big, okay, it can end up being, you can end up getting this weird zigzag pattern, all right? So what's happening here is you've got this bowl surface, and ideally when you take the steps, you're kind of walking down the surface of this of the hill. But imagine this surface that goes, you've got kind of like, if this is the picture of the valley here, you're starting on this side, and you take such a big step that you end up on the other side of the valley, okay? And so now downhill is kind of in the opposite direction. You're taking, the step you've taken so big overshoots the bottom and ends up on the other side, okay? And that's what's happened. We started over here, we took such a big step, we ended up overshooting the bottom and ending up on the other side. And then we take a big step in the other direction, and we end up overshooting the minimum, ending up on the other side. And that's why we're taking this back and forth thing, okay? If you take an even bigger step, it's hard to see here, but basically, again, if this is kind of our paraboloid thing, I'm starting here, I take such a big step that I overshoot the bottom, and not only do I end up on the other side, but I end up higher up on the other side, that my slope is even steeper, okay? And when I do that, it says, okay, because the size of my step is related to how steep the slope is, because I end up in an even steeper location, it says, okay, take a big step in the other direction, and I end up overshooting the bottom, and I end up even at an even steeper location. And so now my thing diverges, okay? It diverges. So it's kind of the problem of overstepping the other side, but I go even farther, that the resulting slope ends up even farther away, and it just diverges and it fails to converge. So your choice of gamma, if you end up with a gamma too big, it might not even converge, okay? And if you have a gamma that's too small, you generally don't run into problems in terms of like convergence, but it's gonna just take like many more iterations to reach convergence. It's going to just converge a lot more slowly, all right? So there's some fiddling around with this, in that you wanted to try to pick as big of a gamma as you're allowed that still converges. You don't, so something like this would be great. When you start seeing stuff like this, this is not a good sign, okay? All right, is that okay? Kind of the basic ideas here for gradient descent. Let's see. In this case, can we let the step size to decay over a certain number of iterations? Because generally we want to go faster when we start and go slower when we reach the bottom. Yeah, okay. So you are proposing basically other algorithms that, that have been developed in terms of changing the size of gamma as the thing iterates and runs over time. And we are not going to get into that, okay? But yeah, Peter also brings up a good point in that because the gradient is steeper in the beginning when you're not near the center, the step size in the beginning are just naturally going to be bigger and get smaller anyway. So even with a constant gamma, you're going to kind of get this phenomenon where in the beginning, the step sizes are big, and as time goes on, the step sizes get smaller, okay? But yeah, there are other algorithms that exist. I don't know the names of them off the top of my head, where you know, you can adjust the gamma as time goes on. And I would say that's a lot more common in kind of Monte Carlo methods, where you're kind of doing this random walk. There's like, I don't know, something called simulated annealing, which is like borrowed from metallurgy terminology, where, you know, anyway, you bake your metals at high temperatures and then you cool them different rates so that the atoms in the metal line up in a certain way. I don't know metal working, but that's kind of the idea there. How are we feeling about this? Do we feel okay? Let me give you your first quiz answer for today. Week 2, Monday, your first quiz answer is E as an elephant. E as an elephant. Okay, I need to hurry up here. Okay. All right, so let's do gradient descent for OLS regression. So first quiz answer, E as an elephant. Okay, so what we're gonna do is we're gonna do gradient descent and we're gonna apply it to ordinary least squares regression, okay? And so the loss function, when we wrote it in matrix notation, is this, T minus XW transpose, T minus XW, okay? So this is our loss function. You've had homework assignments that deal with this, so I'm hoping this kind of feels familiar. We can multiply it by the scalar 1 over n to kind of make it the mean squared error. If you don't have that, then it's the total squared error. This is the loss function that we're using in ordinary least squares regression, okay? All right, so here I can find the gradient analytically, which means we take the loss function and we find the derivative with respect to W0, and we find the derivative with respect to W1, okay? And so this is what it would be, right? So if I expand this and I do this, then this is the gradient with respect to W0, right, which simplifies to this. If I find the gradient with respect to W1, then it becomes this, all right? So this is non-matrix notation. I can do it in matrix notation, and I can just say, what's the gradient of L with respect to W? And I skipped the steps, but we covered this in a previous lecture, and this becomes X transpose T, X transpose X W, right? I'm sorry, minus X transpose T plus X transpose X W. We can multiply it by a constant 2 over n, and that's fine. Okay, so we got, so our gradient is minus 2 over n X transpose T plus 2 over n X transpose X W. Okay, I did that quickly, but I'm hoping, you know, this at least looks familiar from like some previous slides in an earlier lecture that I can just say, well, go back a lecture or two to look, find the slides that show how we found the gradient, okay? All right, and so the gradient descent algorithm will look like this, right? So in matrix notation, it's our current value of W minus gamma times nabla W, nabla F of W, okay? Or we can take our current values of W0, W1 at time n minus gamma times the vector of partial derivatives, partial with respect to W0, partial with respect to W1. Okay, so this is what we have here. All right, so what I'm gonna do is we're gonna just start off with the simplest, a very, very, very simple example, okay? So here are my 3 data points. I've got X is 1, 3, 5, and T is gonna be 4.8, 11.3, 17.2. And if I ask R to find the linear regression model, the ordinary least squares model, it's gonna say it's got an intercept of 1.8 and a slope of 3.1. And this is what the plot would look like. If I have 1, 3, 5, and I plot the data points, these are the data points, and this red line represents the best fitting line here, okay? All right, so here we have a question. It says, sorry, should we add 0 to the LM function because we already have the big X matrix with the first column to be 1? I didn't use the X matrix here, right? I could do, I could have done LM tilde 0 plus big X. I could have done that, right? And that would have worked here. But here I just did the T vector and the X vector, okay? So I could do tilde 0 plus capital X, okay, where I've included the ones, okay, and that would be correct, okay. So anyway, this is what LM is. This is the answer, okay. This is the answer, and I'm putting this here to kind of say this is the answer that we want. We want this intercept and we want this slope, and we're going to see if we can find the same intercept and slope using gradient descent, okay. And so the algorithm is this. Here is the algorithm. We're going to take our current value of W in matrix notation minus a gamma times nabla F of W. And the gradient, okay, nabla F is, you know, the derivative of L with respect to W. And that's this, negative 2 over N X transpose T plus 2 over N X transpose XW, right? This 2 over N is a constant. And when we multiply it by gamma here, I can just kind of bundle in the 2 over N with the gamma, right? So I can just kind of, I can just say, you know, whatever our gamma is, it's gonna be, you know, some value that includes a constant. So I'm gonna just go ahead and drop it when I write my function in R, okay? So as far as R goes, it's gonna take in a W vector, and then it's gonna produce basically negative X transpose T, which is what I have, negative X transpose times the T vector, plus X transpose times X times the W vector, okay? And this is gonna output a vector, and that's gonna be our gradient loss, okay? So this is, I just create a function that's gonna take into the W vector, and it's gonna output the gradient of our loss function. And then as far as the algorithm goes, this is really it. This is really it here. I'm going to just run 1,000 iterations here. I just start some arbitrary starting location. I'm going to start off with an intercept of -1 and a slope of 1.5. Okay, these are, I just arbitrary starting location for the intercept and slope. Okay, I'm going to choose a small gamma just to kind of stay on the safe side, and I'm going to just let it run 1,000 iterations. And as far as the algorithm goes, it's just this one line, right? It's just take your current value of W, our W vector, minus gamma times the result of the loss function, okay? Of the gradient, okay? Of the gradient of the loss function. So I do W vector minus gamma times the gradient of the loss function. That updates the W vector, and then we just repeat this over and over and over again, okay? So is there a specific reason why you did not include the constants in the gradient code? So yeah, it's just a constant that can get absorbed into this gamma term, okay? And I've just moved, yeah, it's like integrating, getting a plus C on each side and moving them onto one side. Yeah, it's just a constant that you can kind of just combine together. So that's what we have here, okay? And so I let this run 1,000 iterations, and after 1,000 iterations, this is the intercept and slope that it figures out. 1.79995 and 3.1001, which is close to the answers that LM finds at 1.8 and 3.1, okay? Now this was a lot more work, okay? But But this illustrates that we can get the right answer by doing gradient descent. Okay, so we get, you know, basically 1.8 and 3.1, just a little bit off. Okay, and I kind of want to show you what this looks like. Okay, so the loss function, I'm going to plot the contour of the loss function. Okay, and it's going to show you the different values of the loss function for different combinations of the slope and intercept. Okay, so when I plot this, the minimum value of the loss function happens where the intercept is 1.8 and the slope is 3.1. That's this location here. Okay, these ellipses, this is a giant kind of ellipsoid bowl that will take us, that has a minimum at the location 1.8, 3.1. Okay, so the minimum occurs where the intercept is 1.8 and the slope is 3.1. And every time you pick a different slope and a different intercept, the loss function takes on a higher value, right? So it's kind of just like, let me pull up. Okay, so here it's like, this represents, I don't know, these are some dots, okay? And, you know, the vertical distance between the dot and the regression line is our residual, and when we square that, this is the squared residual, right? And you can adjust the intercept, and it's going to change the size of the residuals and the total size of the air, right? And if I change the different slopes, we can see how the residuals between the dot and the line will also change, okay? And what we're saying is that, you know, it's minimized in our example when the intercept is 1.8 and the slope is 3.1, but we could try other examples, other things, and if the intercept is -1 and the slope is 1.5, which was my starting location, you know, that's like having something like this, right? Where you have terrible properties, you got huge residuals, and your total sum squared, your total loss is quite big. Okay, so that's what we have here. So okay, and so just kind of showing you, this is what the picture looks like, right? So here the intercept is -1 and the slope is 1.5. There is huge loss, huge residuals between the actual value and the predicted line. So this is like starting off way on, very high up on one of the edges of the paraboloid, okay, one of the sides here. And so when you follow the algorithm, it's going to say, take a step towards downhill, take a step towards the bottom of the hill. And so at the next iteration, it says, don't use a intercept of -1 and a slope of 1.5. Try out this. Here's an intercept of -0.772 and a slope of 2.3, okay? And that changes this line from here to here, okay? And we can see, yeah, that reduces the amount of loss, but it's still a lot of, the residuals are quite big, okay? The residuals are still quite big, okay? And then you take another few iterations, and this is where it is. And we can see already after a few iterations, we're doing a lot better. There's still quite a bit of residual, right? Residual, we know this is not the best fit line because all the points are above the line, but the residuals have shrunk dramatically from here. Just after a few iterations, there's the residual here, and we square that, and this is kind of our loss function. And after more iterations, you know, we're changing the intercept and adjusting the slope. This is what we have. And after a few more, this is kind of the line that we have. And after many more iterations, we're starting to get closer to the location of best fit. Here, our intercept is 1.475. We have a slope of 3.18. And after many more iterations, after 1,000 iterations or so, we'll have an intercept of around 1.8 and a slope of around 3.1. Okay, so this is kind of the path that it takes going downhill. So it, you know, just imagine this very weird shaped, almost like a boat shaped bowl, okay, where you drop it down and it kind of goes down this way and then rolls down the center. Okay, so it rolls down the steep edge first and then it rolls down the center here. Okay. If you have a different size gamma, okay, so again, this is a thing where you end up taking such a big step that you end up on the other side of the bowl, okay, that that you get this weird zigzag. It still ends up converging, but you get this funny behavior here. All right, we got a question. It says, would a decent starting slope and intercept, would that just be the line that connects the first and last points? I mean, yeah, you can start, have different strategies for good starting points. And, you know, depending on the data set, you know, well, how would you just define what your first and last data point is? Is that min X and max X, or is that min Y and max Y, or what, right? Like, depending on your data set, you might have different options for what a good slope and intercept would be. And that's that, right? Obviously, for ordinary least squares, you know, it's silly to apply a gradient descent algorithm. Like, this is already a solved problem, so trying to apply gradient descent is a silly thing. I'm using this as an example of kind of how it's working, so we can kind of learn how gradient descent works in the first place, so that when we apply it to neural networks, which is going to be something a little bit new that I'm introducing, I'm hoping that at least the familiarity of understanding how it works for OLS will make sense, right? So, you know, with OLS, do you choose min X, min, and max X as your starting and endpoints? Maybe, right? But then if you have this high dimensional data set of, like, say you've got 20 X variables, which of your X variables do you choose as your first and last points? And that's it's not an easy thing to answer. And so, you know, I don't know what a good starting slope and intercept would be. You can just arbitrarily pick one, but that may or may not be the best. And so gradient descent will help us find the center, even if it takes maybe not the most efficient path, okay? Here's one a gamma that is much too big. And again, this is a situation where you take a step, you end up on the other side of the hill, but even at a steeper location, and look at what happens. It diverges, and that creates a problem here, right? So this one's no good. Okay, why don't we take a 5-minute break here, and then we'll come back and we'll take a look at numeric gradient calculation and regularization. So we'll pause the recording here. Okay, so earlier we had a question about what do we do if we can't find the gradient or the derivative analytically, okay? And so the answer is there are workarounds, but it will be slow, okay? It can be done. You can estimate the gradient numerically, and it's often recommended that you do it as a way to kind of verify your analytic work, okay? So, so later this week and next week, we're gonna do neural networks, and you're going to find the gradient, you know, following this kind of backpropagation process, and it's hard, and you're not sure if you found the gradient correctly, and so to verify, what you can do is you can do a numeric gradient check. You can find the gradient numerically, and see if you get the same number as the way you did with your analytic tool, okay? So, so, you know, the numeric gradient calculation is simple, but it's inefficient, and it's gonna be slow. So we recommend finding gradient analytically via calculus, and then and implementing the analytic approach if possible, okay? But this is how it works, okay? So the basic idea is that for a derivative, the definition of the derivative is the limit as h goes to 0, right? And if you get rid of this limit as h goes to 0, and you just say, let's use a small h, like 10 to the negative 5 or something, okay? Then you'll get an approximation of the derivative, right? And that's basically all we're gonna do here, okay? We're gonna say if you've got some gradient function here, okay? just pick a small value of h, right? And the gradient is basically the partial derivatives of f with respect to each component, right? So if you have a function of x1 and x2, then your gradient is going to be the partial derivative of f with respect to x1 and the partial derivative of f with respect to x2. Or, if you've got 20 dimensions, then this thing will be, a vector of length 20. But each thing will be a partial derivative with respect to each component. And so here, the partial derivative with respect to x1 is going to be, you add the small constant h to x1 and only x1. Don't add h to both x1 and x2 at the same time. This is a common mistake students make, okay? You add h to only x1, you leave x2 as is, right? And you calculate x1 and the function of f at x1 and x2, and you take the difference between this function, the value of the function after you added a small increment to x1, and the value at the original location, and you divide by h. Okay, you do the same thing, but with x2. You leave x1 the same here, but you add a small h, small, increment here, and you see how did the function change when I incremented x2 a tiny bit, okay? And then you take that difference and you divide by h. And that's it, okay? So you're just doing basically a gradient approximation, okay? Or a derivative approximation, but you're applying it to partial derivatives. And so, if you have a high dimensional function, you've got to do this, for as many dimensions as you have. So just the function that we had earlier was this function. And so we're going to estimate the gradient numerically, okay, on the next slide here. All right, so we're going to just say, let's start at location -5, 4. Okay, so if I plug in -5, 4 into this function, okay, -5 squared is 25, minus 2 times -5, which is plus 10, minus 0.5 times -5 times 4, which gives me plus 10 as well, plus 2.5 times 4 squared, which would give me plus 40. And the function at this location is 85. Okay, that's the value of the function at that location, 85. And then what I'm going to do is I'm going to add a small increment. Okay, I'm going to add an increment of 0.01, which is quite large. Normally we would add something on the order of 10 to the minus 5, but just for illustration, I'm going to add 10 to the negative 2, 0.01. Okay, so basically, again, do it only to one variable at a time. So I'm going to add 0.01 to -5, which gives me -4.99. Okay, and then I evaluate the function. At -4.99, 4, the function ends up being 84.8601. 84.8601. Okay, 84.8601 minus the original value of 85 divided by 0.01, I get -0.1399. Divided by 0.01, I get -13.99. If I do it for the other value, I leave -5 the same, okay? And then I add the increment only to the x2 variable. So this becomes 4, and this becomes 4.01. So I have f at -5, 4.01. This thing evaluates to 85, and this thing, if I run it through the equation, I get 85.22525, okay? And I take the difference, I get 0.22525, divide that by 0.01, and I get 22.525, okay? And if I go all the way back to slide 10, where we calculated the gradient analytically and we plugged in the numbers, we got the gradient to be -14 and 22.5. And here, the gradient we estimate is -13.99 and 22.525. So it's pretty close. Our numeric estimate is pretty close to the actual values. All right, and so this is how you can calculate or estimate the gradient numerically without taking any kind of derivatives or anything like that. You just plug in a small increment, add a small increment to each term one at a time, and you see how much the function has changed. Right? And it's recommended that you do this to kind of just make sure, like, if we, back here, if we weren't sure if we took the gradient, like we did the analytic gradient, and we weren't sure if we did our math correctly, okay, we can do this where there's no calculus involved, no derivative taking, just plugging in some numbers and computing, and we can kind of see, is our analytic result close to the numeric estimate, and they are, and that would give us, that would bolster our confidence in our analytic result. Does that make sense? Okay. Okay. Let me give you your second quiz answer today. Your second quiz answer is C as in cat. C as in cat. Okay, and then we have a question. It says, you forgot to ask, what is the stopping criteria of the gradient descent algorithm? The stopping criteria is whatever you choose it to be, okay? You can just say stop after a certain number of iterations, which doesn't guarantee convergence. It might get you good or bad, okay? Another option is you can say when the new value, the value of the loss function between now and the next value is below some threshold value, right? So you just say, I need to, when it's value less than some epsilon between the current value of the loss function and the next value of the loss function is less than some epsilon, you can choose to stop. So those are generally, that's generally your stopping criteria, but again, you're not guaranteed to converge. And so it may end up running for forever and never reach that stopping criterion. And so usually most optimization algorithms will have kind of an exit thing. It'll say, like, it'll keep track of how many iterations, and it'll say maximum of iterations to run and some epsilon value. And so it will keep running until it reaches the epsilon criteria is met, where the loss function between the current iteration and the next iteration, the difference there is smaller than a certain thing. And then if it reaches that, then it'll stop and it'll say we've converged, or it'll keep going until it reaches some max iterations. You might say max iterations is, 10,000 iterations. And if it hits 10,000 iterations, you say, all right, just stop and say you didn't reach convergence. So that's often what happens. Okay, let's talk regularization. All right, so so this is a little bit completely different topic. Okay, we talked gradient descent, and that will come into play on when we do neural networks. Okay, and then today I'm going to talk or right now I'm going to talk regularization. Okay, and regularization is a way to help us avoid overfitting. And it will also reduce the variation. So completely different topic, so change gears here, okay? So, the problem of overfitting is that we end up modeling odd specifics that exist in our training data, right? So there could be, just by coincidence, when you select your, your random sample and you're gonna say, this is gonna be my training data, there could just be something strange that happens in your training data. And if you overfit, you're modeling something that's weirdly specific to that training data set and not something that generalizes to the population, all right? So cross-validation, we learned that last week. That's one method that helps us avoid overfitting, okay? And then regularization is another method, okay? And what it does is it modifies the loss function itself, and it penalizes complex models. So let me explain, okay? So when we're doing ordinary least squares regression, this is what our loss function looks like, right? It's just the difference. This is the residuals, and then, we square it by, if I do the residuals transpose times the residuals, basically I'm going to get the sum of the squared residuals, right? So this is the sum of squared residuals. I divide by n to get the mean squared error, right? And the best model is, according to ordinary least squares regression, is the model that minimizes the mean squared error, okay? And if we're guided by this principle only, okay, if we're just saying, let's minimize the mean squared error, what could happen is that we end up selecting an overly complex model, right? Because in linear regression, if you keep adding more and more terms, you can end up eking out a higher and higher R squared, right? So if you keep adding more terms to your regression model and you say like, you know, to predict the house of the price of the house, you know, let's take into account the size of the house. Let's take into account, you know, you keep adding more and more and more and more terms, you can eke out a slightly higher R squared and shrink your mean squared error just ever so slightly, right? But you might end up picking an overly complex model, right? And so the classical method is you say, well, let's check if these terms are significant. Let's check our AIC, our BIC, and all of these different things that talk about, that look at model complexity. What we're going to do here is we're going to modify this actual loss function by including a penalty term for the model's complexity. Okay, so this L is the regular loss function, okay, plus a penalty for complexity. And we're going to call this L prime, okay? And lambda is going to be how much complexity is penalized, okay? So lambda can be big or small, and we can say punish complexity a lot or punish complexity a little bit, right? And if lambda is 0, then it's exactly just the ordinary least squares loss, okay? Then this term drops out if lambda is 0 and you have no regularization, right? So this is known as the regularized loss. When you include a penalty term for complexity, that becomes the regularized loss. All right, so this is just an analog or an analogy to real life, right? So, you know, one day, maybe even now, you have to search for a place to live, right? And, you know, depending on where you live, you know, price of an apartment can be crazy expensive and things like that, right? So you might consider, you can say like one apartment, maybe it costs $2,000 a month, but your commute is 10 minutes each way, right? So maybe it's even just like a 10-minute walk each way, and it's lovely, okay? Another apartment, $300 less per month, $1,700 a month, but you've got to commute 40 minutes each way, okay? Commute 40 minutes each way. So if money is the only factor that matters, right? If money is the only thing that matters to you, then you're going to say, I'm going to pick the cheaper apartment, all right? I'm going to pick the cheap apartment with lower cost, okay? But most people value their time, and you know, an apartment with lower rent comes with a penalty, which is the additional time spent commuting, right? And so if you value your time greatly, right, you've got an active social life outside work or something, or you hate commuting or whatever, then you're going to weigh the penalty for the longer commute much heavier. And you're more likely to select the apartment that's closer to work, even though the rent is higher, okay? On the other hand, if you don't mind the commute, okay, if you don't have a lot to do outside of your work hours, right, then the penalty for having a longer commute is greatly reduced, right? And you're more likely to select the apartment with the lower rent, because to you, that extra time spent commuting is not a huge loss, so why not, right? So kind of the true cost of the apartment is going to be the base rent, either the $1,700 or the $2,000, plus some kind of penalty for the commute, multiplied by some preference factor, right? So it's kind of in the same form. It's the base cost plus, you know, your preference and the penalty. Okay, so this is kind of the idea here, and so what we do is we're going to have different lambda terms that's going to decide how much we dislike or don't mind having a complex model. Okay. The apartment analogy breaks down in that we're not going to be using this to compare one model directly with another. Is that here we are modifying the loss function directly, and we are still optimizing the loss function, okay? But when we try to find the best coefficients to use, we're considering not only the resulting mean squared error, but we're going to factor in the penalty term. okay? So this term is can also be written as this, lambda times R of f. R is like the regularization term, okay? And here it's just, I've written it as kind of a complexity penalty, okay? And you can read more about it on Wikipedia. And one thing to note, this is, sometimes students have gotten confused. Even though it's L prime, this is not the derivative of L. I know a lot of times in calculus you use a prime to indicate a derivative, but this is not the derivative, it's the modified loss function. Okay, it's the sum of the original ordinary least squares loss function, which is the sum of squared errors or mean squared error, plus lambda times a complexity factor, okay? Complexity penalty. It's not the derivative, okay? Sometimes that confuses students. All right, so here's one way we can measure a model's complexity, right? So here, let's say we have two possible models. Model A fits a fourth order polynomial and model B fits a fifth order polynomial, okay? So we know that the fifth order polynomial is going to be more complex than the fourth order polynomial, okay? The fifth order polynomial will have this linear regression equation. It's got W0, W1, W2, W3, W4, and W5, and W5 is multiplied by x raised to the fifth power. Okay. However, if we force W5 equal to 0, okay, if we force W5 equal to 0, this becomes equivalent to the simpler fourth order polynomial, right? So these two terms, if I just force W5 equal to 0, then this is going to be the simpler fourth order polynomial, okay? And so one possible way to measure model complexity is to count how many non-zero coefficients we have. So how many coefficients do we have that are not zero that can be used as a measure of model complexity? All right, one problem with this though is that trying to count the non-zero elements is very, very difficult to optimize, okay? The loss function is not convex, and you have to consider all possible permutations of which elements in W are non-zero, okay? So you can have, you know, more, if you have like 10 terms, you know, there's 2 to the 10, 1024 different permutations or combinations of which ones are zero and non-zero. And it gets complex very fast, okay? And not only do you have to consider all 1024 different combinations, but you also have to find the values of W themselves. So optimizing this is very, very, very challenging, okay? So we don't even bother trying to do that, okay? So what we're gonna do instead is, rather than the L0 norm, we'll use the L1 norm, okay? So instead of counting which elements are non-zero, we're going to sum the absolute values of the elements in W. So we're just going to take each W term and we're going to just add them up. We're going to take the absolute values and add them up, okay? That is way different from how many terms are non-zero, but it could work, okay? So so non-zero values, if a W term is not zero, like W sub D is not zero, it's going to contribute to the penalty factor. And, you know, larger values of WD will contribute even more to the penalty factor, okay? If a coefficient is 0, right, then the variable is not counted and does not contribute to the penalty factor. So that's a good thing, right? And so when you try to optimize the loss function, then any reduction in the mean squared error must be greater than whatever offset there is by including the W term, okay? And this is known as lasso. This is known as lasso regression, okay? And then there's another, and this is ridge regression, okay? And you take the W2, the L2 norm, and this will be the basically the sum of W squared, okay? The L2 norm squared. So it's the sum of the squared values in W, right? So you take each of the W elements and you square them, and larger values of W are penalized heavier. This is the penalty factor. Large values of W are penalized heavier. Smaller values of W are penalized less. And this is known as ridge regression, okay? And a side effect or one effect of ridge regression is it prefers when values in W are similar in size to each other, okay? And it feels strange, maybe I'm doing this too fast where it doesn't feel strange. I'm just presenting these things to you. But you might, maybe you were on board here when I said, let's count how many non-zero elements we have, non-zero elements of W we have, and that measures model complexity. But now I'm talking about adding up the absolute values of W or adding up the squared values of W. And I'm saying that's going to count as the penalty. And that maybe that feels weird to you, right? Okay. Which method sends coefficients to absolute zero and which one just makes them really, really small? So lasso will send them to absolute value zero, and then ridge regression will just make them really, really small. That's one thing that happens, okay? So you might wonder, how does the size of a coefficient, we're not just looking at whether it's zero or not, but we're measuring the size of the coefficient. How does that measure complexity, okay? So measuring complexity based on the sum of the coefficients, or I should say sum of the absolute values of coefficients, or the squares of the coefficients might seem strange, right? If two models have the same number of variables, aren't they equally complex? You might have this objection, right? So why is one model considered more complex if it just has a bigger coefficient than another, right? So you have two models, it's got the same number of terms, one has a bigger coefficient than another, and that one's considered more complex than the other, right? If bigger coefficients mean more complexity, can't we just change the units, right? And that will shrink the coefficients and reduce complexity? You know, with all of these objections, this doesn't seem to make sense, right? And these are totally valid objections, right? And so I'm going to try to address them, right? So, you know, one thing we'll say like, well, if I want to reduce the size of my coefficients, you know, let's just measure things in like kilometers rather than centimeters, right? So, because if I measure someone's height in kilometers, so this person is 180 centimeters. If I measure their height in kilometers, then they are, what is it, I don't know, 0.018. I don't know how many. It's a tiny thing, right? And so the coefficients. Oh, actually, the coefficients will end up being huge. So I'm sorry. Let's measure their height in like millimeters or nanometers, and then you know their the coefficients will end up being tiny, right? So so one thing we want to do is it's almost always recommended that you center and standardize your x variables, right? So centering means you add or subtract a constant so that the mean is zero. So you just take the mean of the column and you subtract the mean of the column from the column so that the mean of the column is zero. And then standardizing means multiplying all the values in the x column to by a constant so that the standard deviation is 1. Okay, and standardizing variables addresses the concern that using different units will affect the size of the coefficients. Okay, after centering and standardizing, all variables will have mean 0 and variance equal to 1. Right. An alternative is to scale the x so they go from 0 to 1. Right. So this is used if the function can't accept negative values. So rather than having a mean 0 and standard deviation 1, you can scale them so they all go from 0 to 1 in case you're using like the log function and you can't have a negative value. Okay, but then how does the size of the coefficient measure complexity, right? And I argue that the size of the coefficient does measure complexity, right? So let's say we have two competing models, both and the models both use 4 variables. Both models have the same coefficients for x1, x2, and x3. Okay, model A has a larger coefficient for x4, let's say W4 equals 1, and model B has a tiny coefficient for x4, let's say W4 equals 0.01, okay? So with the exception of W4, which is 1 and 0.01 for models A and B, models A and B are exactly the same. So the W1, 2, and 3 are all the same for x1, x2, x3, right? So both models use 4 variables, but I argue that model B is less complex than model A because it has a smaller coefficient for x4, right? Okay, so these two models are exactly the same. The only difference is that the coefficient for W4 is different. This one is bigger and this one is smaller, okay? And the reason for this is that a small coefficient for variable means changes in that predictor variable, and changes in x4 has little impact on the outcome variable, right? So if model B has a tiny coefficient for x4, then it's putting less importance on that variable x4, basically, right? Even though model A and model B use the variable x4, model B is much closer to ignoring x4 altogether, right? So model B is almost ignoring x4, even though it's not. And because it's that much closer to ignoring x4, it's the simpler model, right? So here's a silly analogy, right? So imagine you've got 2 students and they both are involved in several clubs on campus, right? And we know clubs can be very time consuming, right? Let's say one of them is fully invested in all of their clubs, has a super busy schedule, lives a complex life, right? The other student perhaps is involved in a bunch of these clubs, but is only marginally invested, right? So, you know, they feel like, you know, they don't feel like going, they skip a meeting, right? There's an event going on, they don't participate, right? So they're only marginally invested, right? So I argue that the student that's only marginally invested, that student's life is simpler and less complex. I don't know if you guys agree, but I would say, you know, if you're putting less importance on something, then the model ends up being simpler because you're that much closer to ignoring it, right? And that's just an extreme case, but just we can expand on this and say, you know, the size of the coefficient is a measure of complexity, right? Especially after we've standardized all of our variables, right? So that units is not a factor, okay? So the weight placed on each predictor variable after it's been standardized can be used as a measure for how complex the model is. All right, so here I'm going to try to illustrate this with some simple data in 2D, okay? So we've got x1 and x2, all right? They're on the same scale, so I won't bother centering and scaling them, okay? They both go from 1 through 4 here, all right? And the true target, the true output is going to be 1.5x1 plus 0.5x2, okay? There's no intercept in this thing, all right? And so the true output, the coefficient for x1 should be 1.5 and the coefficient for x2 should be 0.5. I'm going to add some random noise and I fit an ordinary least squares model, okay? And the coefficients for this end up being 1.458 and 0.453, okay? And that's the effect of just the random noise that gets applied to our observations here, okay? So this is the best coefficients according to ordinary least squares regression, okay? And so this is if I use LM, okay? Here I just want to demonstrate using Optim, okay? So this function measures the ordinary least squares loss, okay? It just calculates t minus xw transpose times t minus xw, okay? Sorry, something strange just happened. Let me pause the. Okay. All right. So so here I'm just saying this is the loss function, and we need to optimize this. Okay. And so I plug the loss function into the function optim. I start off with some arbitrary location of 0, 0. And then by using optim, we find the coefficients for x1 and x2, and these line up with the coefficients that LM has found. Okay, is this all right? So here I'm just using, here's our OLS loss, okay? And I plug that into Optim to get the coefficients that minimize the loss function. All right, is this all right? Okay. Did I give you, how many quiz answers have I given you? 2? 2, okay. I'll go ahead and give you the third quiz answer, okay? Third quiz answer today is A as in apple. Third quiz answer is A as in apple. Okay, third quiz answer is A as an apple. Okay, so okay, so here is, so by saying, we asked R to use Optim, and you guys used Optim in your homework, I hope, and in that we say, okay, find the coefficients that will minimize the loss function. Okay, so what I'm going to do now is I'm going to modify the loss functions that we're going to optimize, okay? So here, oh, okay, before I get into that, this is the contours of the loss function. So this is what the ordinary least squares loss function looks like. It's a bunch of ellipses, and the minimum happens right around here at 1.5, or it's actually at 1.458 and 0.453. Okay, and so here I'm going to modify the loss function by calling, by naming it the L1 loss. This is the lasso loss, and what it is it's the OLS loss plus lambda times the sum of the absolute values of the coefficients. Okay, so we take the absolute values of the coefficients and we add that here. Okay, so we're going to take the absolute values of these coefficients, we add them on, multiply it by lambda. So I'm just doing this, okay? I'm just taking the absolute values of W1 and W2, adding them up and multiplying it by lambda, and I'm adding it to the OLS loss. Okay, I'm adding it to the OLS loss, all right? And then I plug that into Optim, okay? And I say, all right, if I plug in lambda equals 10, what is the values that it finds, right? So the coefficients that worked out for the best for the ordinary least squares was 1.458 and 0.453. As I increase my lambda, going from lambda from 10 to 50 to 100, the coefficients end up shrinking, okay? They go from 1.458 to 1.436 to 1.345 to 1.231. These ones start at 0.453 to 0.430, 0.339, 0.225. As I continue increasing lambda, the coefficients continue to shrink until I have lambda at 500, and these two things, the coefficients end up equaling 0. Okay. So let me just show you what is happening. Okay. So this represents the contours of the loss function, and the red is the coordinates of the slope parameters of W1 and W2 that minimize the OLS, okay? When I set lambda equal to 10, the W1 and W2 that minimize the loss function is offset by a little bit. As I increase lambda to 30, it gets a little bit bigger, and lambda 50, as lambda gets bigger, then the offset goes down. This is the best fitting set of W1 and W2 parameters. And we can see that they get moved down and down and down. Remember, what the lasso function is doing is it's penalizing the size of the coefficients, right? So as I increase the lambda, and is lambda an arbitrary value here? Yeah, it's chosen as a value kind of indicating your preference for whether you want a complex model or not, okay? So as I increase my lambda, I'm penalizing more complex models more heavily, right? And again, complex is measured by the size of the coefficients. So as I say, I'm going to penalize complex models, the solution is to shrink the size of my coefficients, because if I shrink the size of my coefficients, I have a less complex model. So as I increase lambda, the coefficients shrink down until one of the coefficients actually becomes 0. And then as I continue increasing the lambda, that other coefficient gets pulled down to 0 as well, okay? Until I get, basically the simplest model is having coefficients of 0 and 0. But in the beginning, we're not penalizing a complex model very much. And as I increase the penalty of the complex model, complexity being the size of the coefficients, as I increase that penalty, the coefficients want to shrink down until one of them becomes 0. And then as I continue increasing the lambda, it keeps shrinking. So it says, would this model choose a model with 3 variables with small coefficients over one with 2 variables? And okay, so what lasso does is it kind of penalizes both W1 and W2 equally. And that's why they move in a diagonal direction, because when it applies a penalty to W1 and W2, they're penalized equally. And so it kind of, W1 shrinks by the same amount as W2. W1 and W2 shrink by the same amount. And so what lasso ends up doing is, if you start off with four things, all 4 are going to get kind of penalized equally until one of them turns into 0, and you're going to be left with 3. Okay, so this could happen where here we had two coefficients back here, and as we increase the lambda, one of them gets driven down to 0, and this one, so the W2 got driven down to 0, and W1 is not a 0 thing. So this is basically a model with only one coefficient. Okay, and as I continue to penalize this, that gets driven down to 0 as well. Okay, so yeah, Matthew says, I would say more variables is fine if the total sum is still smaller somehow. So the thing is when there's rarely going to be a situation where 3 variables with small coefficients will outperform 2 variables with bigger coefficients when you're taking into account the OLS, right? So you have to take into account we're not just penalizing, we're not looking at the penalty only, okay? We're not looking at this thing only, right? This thing only, yeah, you can have a situation where you have 3 variables with small coefficients where the penalty term is smaller than having 2 variables with bigger coefficients. That's a situation that could happen. But when you take into account the OLS, the ordinary least squares loss, then a situation where you have 3 variables with small coefficients will almost certainly have worse OLS performance than the 2 variables with the bigger coefficients. Okay, so generally that when you do lasso, you're not going to end up with more models, more variables or something. Okay, so this kind of sums up to what I said. Where you see the travel diagonally, which means that the slope and the intercept, sorry, it should be the W1 and W2 parameters decrease by the same amount as lambda increases. Okay, and both parameters decrease until the same amount until one of them shrinks to 0 or hits an axis, and when that happens, we can't decrease the penalty further. So only the non-zero coefficients continue to shrink. For ridge 2 regression, oh, I'm missing a squared value here. Sorry, there should be an extra 2. I have a typo I need to correct. It should be lambda W L2 norm squared. Okay, there should be a squared term here, sorry. And this should say the L2 norm squared is the sum of squares W. I'm missing a squared term there. Let me jot that down, slide 84. Okay, so here we're taking the OLS loss and we're adding the sum of the W2's, the W's squared. Okay, so we take the W's terms and we square them and we're gonna add that on, multiplied by lambda, okay? And then, so we're gonna try optimizing this, the OLS. We take the OLS loss plus our penalty term, okay? And then, and again, I won't bother showing you going through all of these numbers line by line here. You can look at these numbers. I want to show you here. Okay, so again, the red dot is the OLS loss. Okay, when I have lambda equal to 1, this ends up being the blue dot is where the best fitting parameters are. W1 and W2 end up here. Okay, which is interesting. It's not moving diagonally towards the axis. It's moving up this way. And watch what happens as I increase lambda. Here's lambda equals to 5. It jumps up. It goes up, 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 and then it moves in this kind of arcing motion here. Okay. I don't know if Zoom is fast enough to keep up with my clickings of these things, but it moves in this interesting thing where it's the red dot starts here, and then it goes, kind of forms this arc towards, like if the origin is over here, it goes up towards this diagonal line, right? There's a diagonal line where W1 equals W2. It goes up and then it dives down. So it kind of goes up and then it dives down. All right, so what's going on here? All right, so what's going on here when it's doing this? All right, so what's happening is that as lambda increases, the optimal parameter values travel towards that line W1 equal to W2, okay? And then when it gets close to that line, that blue dot gets pulled towards 0, okay? And so when you square coefficients, bigger values are penalized a lot heavier than smaller values, right? So, so what it's going to do is it's going to shrink the big values first, right? So if you shrink 11 to 10, your complexity value goes from 121 down to 100. You're saving 21 points, okay? If you shrink 3 to 2, okay, even though you're shrinking the same amount of 1 point, 11 to 10 and 3 to 2, your complexity from 3 to 2 goes from 9 to 4. You're saving only 5 points, okay? So shrinking from 11 to 10 saves you 21 points. Shrinking from 3 to 2 saves you only 5 points, okay? So when you have the ridge regression and you're looking at the squared coefficients, it's going to penalize the bigger coefficients first, okay? And so, however, what happens is shrinking not the intercept. Sorry, I don't know why I said this. Okay, the larger coefficient, W1, just ignore this thing, the intercept, and ignore these term slopes. Okay, shrinking the larger coefficient, W1, will end up causing the ordinary OLS loss function to grow, right? So, because the OLS is how well do your dots fit the lines and stuff. Shrinking the intercept will cause the OLS function to grow. So, what can happen is, even though we shrunk W1, we can offset kind of the increase in the OLS by actually increasing W2, right? So W1 is the bigger coefficient, okay? W1 starts off here, it's the bigger coefficient. And what we're saying is that when we shrink W1, okay, our OLS function does worse performance, and we can actually counteract the effect of our worse performing OLS by increasing W2, okay? So we're kind of compensating for our worst performance by increasing W2. And because W2 is smaller to begin with, okay, because W2 is smaller to begin with, the increase in W2, it technically does increase our penalty term, but it increases the penalty term only by a little bit, okay? And so, so in this case, what we see is we shrink W1, but we end up increasing W2, at least in the beginning, okay? And so that's what we see. We see W1 shrinking, but W2 increasing until it reaches some point where now we want to shrink both W1 and W2 as the penalty increases. So that's what we have going on here. All right. And so why do we bother with all of this? Okay. So one thing is that the regularization, it helps combat overfitting. Okay. And it also reduces the variance of the parameter estimates, okay? So when you think of some kind of random data set and you estimate the slope and intercept parameters, you have to take into account that that data is random, okay? And so if two people are studying the same population and two people gather different random samples, you know, their slope and intercept, their coefficients are gonna be different, right? There's going to be variation in their parameter estimate. So this person gets this slope and this intercept. This person gets this slope and this intercept. Okay, they're going to be slightly different. And if there's great variation in the parameter estimates, that's not a desirable trait. Okay, I'm going to run out of time here. Okay, so regularization will reduce the variation in the parameter estimates. Okay, I think we'll. I'll have to save this section for Wednesday. It's just a few pictures. It'll be quick. Okay. So we'll save this till Wednesday. But you should be able to get started on this week's homework with at least this. And I know you're still wrapping up homework 1, so we'll have that. And that's it. We'll end there today. I think I gave you all 3 answers for today's quiz, right? Okay. So we'll end here for today, and we will see you guys on Wednesday. All right. So thank you very much.